The point of this talk is to introduce these two codes I developed. They are generators for initial conditions of galaxy or cluster simulations, completely written in Python and publicly available on GitHub. So to generate a galaxy or a cluster to simulate, you're dealing with a discretized system. You have n particles. You have to determine the positions, which is easy given a density profile. The velocities, it's not easy. It's by far the hardest part because the distribution function for the velocities is generally not analytical. You have to calculate it numerically, and I don't have time to describe the algorithms in detail here. And the temperatures is also easy because for a galaxy cluster, the intercluster medium temperature profile will be given by the hydrostatic equilibrium equation. And for a galaxy, you just set up an isothermal disk. And the codes write the file in the Gadget2 format, and which recently started working with Ramses as well. So this is an example of simulation ran in Ramses with initial conditions generated with GaussStep. The components are these: a dark matter halo. The last three ones are collisionless, and there is also a gaseous disk, which is generated as a system of particles because it's a gadget initial conditions file, but it's transferred into the AMR grid in Ramses using a patch called dice patch. These are the flags the code has. You can generate a galaxy without gas if you're interested only in stellar dynamics, for example. It uses multiprocessing for calculating the potential because the velocities, the distribution function for the velocities depends on integrals which have a potential somewhere. So you have to calculate in a grid to estimate these integrals. And well, this is the most important thing to mention. And the other code I developed is this CluStep. It's the same thing, but for a spherical galaxy cluster simulation. Only two components, a dark matter halo and a gaseous halo. The density profile is a Denning density profile, which reduces to a Hernquist if you set gamma equals 1. If you set gamma equals 0, it's a profile which does not diverge at r equals 0. It has a core, like a beta model for the intracluster medium. You can choose between one or the other. A profile with a core has a cool core. The temperature decreases near the center, while the Hernquist will go up. The Hernquist is quite simple with the Navarro-Frankel-White profile, if someone here is not familiar. And these are the flags. You can generate a galaxy cluster without any gas, or you can handle the dark matter as an external potential and not include any dark matter particles. And for instance, you can alter gadget to include an external potential to represent the dark matter and simulate only the gas to reduce the computation cost in some situations. And I think this is it. If someone the codes are available on my GitHub page, and if someone wants to hear more about the algorithms that are used here, you can talk to me. Or if you want to use the codes but you need a different feature than the ones available, we can implement during this week. And I think that's it.
Daniela's up next. And then Erik T.
Oh no, I changed my title. Alright, I'm going to talk about something that has not much to do to the science, but it has something to do with this meeting, because the organizers told me that they used our tool for this meeting. So I'm going to talk about how you select participants for a workshop, and how you were all basically selected for this workshop. And so this started with a really practical problem. Was when I organized Astro Hack Week last year, I got 168 applications for 50 spots, and I sat there going, what the hell do I do now? And my office mate Brian, who's very good at maths, turned around and said, you're in the Center for Data Science, figure it out. And the objective that we had was to be really diverse, and that means diversity in academic seniority, in pre-existing knowledge, and academic subfield, but also sort of demographics like gender. And if you have 168 people and several categories, you just can't do this in your head. We also kind of wanted to keep some of the human biases fairly small and kind of find the optimal set of participants that match these criteria to really do that. So that's what we did. It turns out it's a discrete optimization problem. You minimize something called the KL divergence for each category between some participants and some targets that you have. And that finds you the sets of participants that you will overall get as close to your target distributions as possible. For example, your target distributions could be you want 30% grad students and 30% postdocs and maybe 20% faculty, and then undergraduates and others, and however that comes up to 100%. But not only that, maybe at the same time you also want to optimize over other categories and globally find a maximum. You can find that here, and I was just going to show you really quickly if I can find where I put it. No? Okay, since it vanished, I won't show you, but you can ask me.
Is it one of the desktop that shows up on that?
Possibly, but I don't really have time, so Uh-oh. Right. No? Oh, there we go. You can run this as a server, and then you get a kind of nice website, and you can put an input, and you can choose a file. We have a test file with like not real data because everything else would not be, ethical. And then you've got all your possible participants in here. And you have sliders to set sort of your target ratios. And then you say, I want, 30 participants, and you say go, and it highlights all the participants that are selected. You can also run this as Python code directly, which I think is what the organizers did. And sort of very briefly, the thing that I'm really interested in is actually the applications. So one thing I want to say, it's useful for any problem where you have acceptable applications and the number is larger than the available jobs, slots that you have. That of course you could do too. You do want to pre-select for overall suitability. I don't think you can do that with our algorithm. That's not what it's assigned to. It requires organizers to really think carefully about their selection procedure and target criteria, and I think that's a big feature. It's still not objective because you still set targets, then that's still your choice, and also you choose categories, and that's not necessarily objective choice, but it does increase transparency and accountability. So you can use this to increase diversity. We're not sure whether it increases imposter syndrome or not. I would love to talk about any of these with you. And we kind of need help for a lot of things, especially for the JavaScript interface, which is maybe not the right thing to say at this meeting, but anyway, thank you.
Oh, 2 Eriks in a row.
Yeah.
It's about the one.
All right, so I just want to talk for just a little bit in a completely different official hat that I'm used to talking about in these sorts of things, about an effort that's going on right now at Space Telescope. to leverage sort of this whole community into providing tools for JWST, or possibly the other way around. Right? That's the fun thing about it. What does JWST have to do with any of this? Well, the key element here is that, in fact, it's been very clearly stated at a mission level that all data analysis tools for the James Webb Space Telescope will be in Python and using sort of the AstroPy ecosystem, right? So that's something we should all really know, right? JWST, the largest single line item in the astronomy budget for the foreseeable future, is using the Python AstroPy ecosystem. So the specific thing I'm going to talk about today is the particular mechanism by which JWST is trying to get more plugged into our ecosystem here. It's this data analysis development forum. So there's a clear aim for Space Telescope to be involved in this Python ecosystem, and one of the large goals of this forum that I'm talking about is to enable more interaction between the community and what's going on at Space Telescope. I would say, off the record, that has not really happened very well, at least so far, but hopefully some of you will be interested in getting involved in this community effort, and we can change that. So what does this forum actually end up doing? Well, in practice, what it means is at Space Telescope, there are coding sprints that last about 2 weeks. There's a little bit of preparation meetings beforehand, and then a little work before and after that keep going depending on everyone's availability. But the basic idea is there's 2-week-long sprints on some particular topic. They're at the beginning of these sprints and sort of shortly after the end of these sprints, there's usually a larger forum where currently it's people in the science staff from Space Telescope, but ideally more people from remote institutions like any of you here would start getting involved in these fora. But you can also be involved in the sprints themselves if it's something that really overlaps with your interests. Speaking of overlapping with your interests, here's some examples of some of the sort of sprints that have happened so far. There was one on interactive spectral analysis. Actually, you'll be hearing more about one of the specific pieces of software that came out of that from Pelion tomorrow. I think tomorrow. Yeah. Well, at some point in the near future, depending on how much time I have, you might hear from me about another one of the sprints. But there's a whole bunch of stuff going on. Is the key point, right? Things you need to do to analyze JWST data is what it amounts to. But that amounts to analyzing almost all kinds of astronomy data because there's a spectrograph and there's an imager and there are all kinds of new fancy stuff involved in that. That's basically what I just said. So the key idea here is that input from the community is welcome, and in fact, it's part of the whole point of the thing. If you think you might be interested in getting involved in any of this, you should go to maillist, that's 2 L's, maillist.stsci.edu. I'm sorry, it's a terrible interface, but you have to look for JWST_DADF. That's probably part of the reason why there's not much community involvement. Let's not worry about that for now. You talk to me. You can also email me. That will also work. You can also, if you're interested in just looking at some of the things that have come out of this forum, you can go to the Space Telescope GitHub organization, which is where almost all of the code ends up. There's repositories there. You can make issues, pull requests, all the standard stuff. That'll at least give you some sense of what's going on. Let's see. How much time do I have?
1 minute.
Okay, then I will give you a very quick sense of one of the most recent one, which was about adding to the PhoteUtils package, right? The AstroPy PhoteUtils affiliated package. Oops, that's the wrong. Wait, that was a minute?
Now you have a minute left.
Ah, okay. Okay, the adding to the PhoteUtils affiliated package to make the PSF photometry part of it actually work and sort of be compatible with the new AstroPy modeling framework. So the key idea is you can use, this is all new stuff that was added as part of this most recent sprint. You can generate fake stars with, let's see, where is it here? You can subtract the PSF stars and you get indeed a blank image like you would expect to see. Let's go a little bit further down. Oh yeah, it gives you AstroPy data tables out to tell you where these stars are that you found using PSF photometry. But the key point, is it there? Sorry. This one will do. The key point is that you actually do the photometry with this like one line of code. right here, right? This is a line of code that does PSF fitting photometry. And this is the sort of thing that, in fact, you may end up doing with JWST because this was developed as part of this this community data analysis development forum. So, yeah, I guess that works for now. Another Erik. Another Erik.
Yeah.
A better Erik.
Let's see.
A different Erik. There you go. Taller Erik. Yeah, taller Erik, not Tollerud, taller Erik.
Taller Erik.
Yeah.
And mirror the built-in display. Hello, hello.
Is it plugged in? Sometimes it falls out.
There we go. Yeah. So some of you have seen this already. You can check your mail or whatever. Some other people haven't seen this, and I've heard some people saying, what is Ginga? If you've been kicking around for a few years in the Python astronomy community, you've probably heard a vague reference to Ginga, which is a toolkit for building scientific viewers. And some people think it's kind of a DS9 replacement, but it's really not. It's a toolkit to allow you to build a custom viewer with what we hope to be good performance for interactive type activity. So a lot of people are building sort of tools for doing data reduction, that kind of thing with it. One of the recent developments that we've been working on is getting this to work with the web. Of course, there's like a half a dozen different kind of web browsers, fits browsers in a web page, but the thing that's interesting about this maybe is that you don't need anything really installed on the client side, and you can run this entirely out of an HTML5 compliant browser. So what I've got here, there's a page I'll show you in a little bit, but I've loaded up a viewer and I've started it up in this separate window here, and you can see there's actually pretty decent performance. You can scale, you can rotate images, you can change color maps, all the sort of things that you'd expect to want to do. You can scale the image, right? And what's neat is you got two-way interactivity with the notebook. So here I've loaded that file into the viewer from the notebook, and then I can just capture the screenshot from the viewer right there. Now I can also do things like if I set a pan position here in this viewer, then I can ask about that position. I can say, well, that's the coordinate that I had, and here's the WCS of that. I can set any of the parameters like the cut levels or the scale. I can also plot things on it. So I've added a canvas, and now I'm going to set the draw type to be a point, and I'll go ahead and draw a point on here. Whoops, got to select this first. Draw a point right here. Can you see that? And where am I? Where was I? Okay, right here. So let's find out what that point was. There it is. Find out the RA deck of the point. You can grab the NumPy data array straight from the image. You can import AstroPy and do all the lovely things that you do with AstroPy or any of the affiliated packages on the data.
Can the data be remote?
The data can be remote. In fact, this can be running on a server somewhere. And what's cool is that two people can be looking at the same URL and they will see the same thing, even in two different sites.
Can they both edit it? Can they both move it around?
If you ask me questions, I'm not going to finish my... Okay, so let me just go through and then maybe if there's time. So let's keep moving here. And so what I want to do is show just, and let's go back to the standard color map here. I'm going to set the draw type to be a rectangle, and I'm going to go ahead and just surround a set of stars here. And then what I'm going to do is I'm going to use some of this machinery to grab the stars, and I can look at some of the information about it, and then I can draw circles around those stars, right? And then I can capture that right there in my web page. So this is a great tool also for students, for teaching, for showing some data reduction thing. You can open up as many of these viewers as you want, and because they're all part of the same Python session, you can load different files into different viewers. So there's a lot of kind of interesting possibilities. If you're interested, here's the URL right here at the top. You can download this notebook. Actually, the notebook also comes, if you clone the most recent Ginga, it's in the examples folder inside there. If you have any questions, I'd be happy to talk to you about it or show you some features. It is that I wrote.
Okay, I want to talk to you, give a defense of extreme openness. And what I mean by extreme openness, I think we're all here because we know the benefit of coding in the open. All these things help with collaboration, sharing, visibility, reproducibility, all this stuff. But why not do all our research in the open for the same reasons, right? And what I actually mean by this is when you're starting a paper, start a GitHub repository in public and put your initial LaTeX template in there and start writing, commit it all there. And I want to give you a little case study on this. I actually did this with my most recent paper this past summer. We wrote this paper, and it was on GitHub in the public in day one. This was a paper exploring an extension of the Lomskargel periodogram to multiband data, and you can look at that URL and see what's there. And if you click there, you see this is our GitHub repository. We have steps for reproducing the paper from scratch. We have steps for building the paper. But the very cool thing is, if you click right here, this is a website that has the current PDF build of the paper. And this website is actually, every time I commit to the repository, it spins up a Travis CI job that builds the website, builds the paper, and commits it here. And if you want to know how to do that, there's this thing called GH Publisher that Phil Marshall worked on. And that's what it's all based on. So it's awesome. But the cool thing about this, too, is that there's this button, Send Feedback. And to complete the loop, if you click on that button, it goes back to the GitHub Issues page, of course, right? And so you can put an issue on this paper when I'm in the process of developing it, before it's been even submitted to archive. And it turned out someone actually did this. If you click here, 3 people did this. The one that's still open is this one right here. And you look and you see that this J. Scargill fellow decided to take a look. And yes, this is Lomskargel, Jeff Scargill. So I was stoked when I saw this, right? And he had this interesting thing. And I actually ended up doing some modifications to the paper because of that. And we got in this long discussion about various pieces. And this is science, right? This is how science works. You talk with collaborators, and this is peer review in the open before we'd even finished the paper, which I think is awesome. Now you're going to tell me, Jake, I can't do this because I might get scooped, right? And it's true, this is an issue, but if you think about what scooping is, you're worried about people publishing what you're going to publish before you publish it, right? But let's look at the definition of publish. It means to make generally known, to make public announcement, to disseminate to the public. Putting work on GitHub is publication. And once you've published something, there's a name for scooping. It's called plagiarism. So I don't think we need to worry about this, because when you put it on GitHub, your work is published. But then you say, but Jake, would you do this if there were any real competition? And I'm going to say, yeah, if you look this past summer, there were 3 papers, and it's uncanny. If you read all 3 of these, they basically are solving the same problem with slightly different methods, using the same test data set, the Sloan Stripe 82 R Lyra candidates. And they were all published within about 3 months. And I thought this was really, really interesting. We were in the open, and the cool thing is, we sort of got wind of these two projects and were able to email them and say, hey, look, we're working on this. And they ended up citing our paper before it was even finished, right? So the citations actually happened. And so you might ask, Jake, how did this turn out? Well, if you look at this and you look at that, you know, not that I'm keeping track. I think doing things in the open is really helpful, so be open. And that's all I have to say.